Okay, let's dive right in. Welcome back. I hope we had a great weekend. So today is our final day on apportionment. We have spent the last 3 classes on apportionment. We started with something called Hamilton's method, where we gave out the extra seats based on the residues, right? The decimal part and what was left over. We did Jefferson's and Adams. For Jefferson, which way did we round? Down. For Adams, up. For Webster's, conventional rounding, which sometimes went down and sometimes went up. And then Huntington Hill was that really crazy kind of rounding based on this thing called the geometric mean. So those are the 5 apportionment methods that you are responsible for. We're not going to see any new apportionment methods today, but we will talk about something called the quota rule and paradoxes and try to kind of make some sense as to which of these 5 might be the best according to kind of fairness ideas. This is our last day on apportionment. Then you see we'll spend 3 days in chapter 9 talking about sequences and in particular population growth and how sequences relate to nature. And then we've got 1 more day about nature, something called the Fibonacci numbers. So we're basically like halfway to the material on the second test. Zeke? 3 tests. Yeah. And technically, so there are 28 classes altogether, and today we are on class 14, so happy mid-semester. This is exactly the middle for Tuesday, Thursday classes. Okay, so jumping into page 24, let's go up to the top. Can we start with Jeff for number 1? Thank you. Zeke, number 2. Okay, so that hopefully seems reasonable. Here's this example. Can we go to Megan, for example? Everybody buy that that would be, those are the 2 reasonable choices if you're at 138.29. All right, keep going, Megan. Okay, so our first question is number 3, Sarah. Okay, so do we remember Hamilton's method? Let's take a look at this row. We've seen this Parador example many times. But suppose that that was our, that's the standard quota right there. To decide how many seats to give out, do you remember for Hamilton's method, we would give everybody their lower quota to start, right? We round everything down just automatically. And then how many seats are left over in this case? 4 left over. So 4 of these 6 states are about to get 1 extra seat each. Who gets the first extra seat? Is A, because that 0.92 is the biggest of all the residues, all the remainders, right? Those decimals. And so A would get 1, and then I don't know who else. I guess D would get the next one, and then maybe F would get the next one, and then B would get the 4th one. And so, so some of these guys would go up by 1, and some of them would stay just where they are. Is it possible for anybody to go up by 2 using Hamilton's method? Right, we round everybody down, and then some people get 1 extra, but nobody would ever get 2 extra. And is it possible for somebody to get less than their rounded down number? No, again, we start by assuming everybody gets at least their rounded down number, and then some people happen to get 1 more. So in some sense, Hamilton's method is good, and that the answer is no, it can never violate the quota rule. No matter what you do, everybody's going to get either their lower quota or upper quota, no more and no less. So that seems good. But in number 4, this table that's filled in here actually uses Jefferson's method. And we remember Jefferson's method rounded everything down. And then we ended up having to use a modified quota, which we did here. I'll highlight it in green. And if we take all those numbers and round down, because that's what Jefferson's method does, we get that. And we see, fortunately, we got exactly 250. Great. So does anybody see a problem looking at the yellow numbers, which is like the exact fair share, and then the bottom green row? I'll erase this middle green one here. Looking at that bottom green one, where is the problem? Does everybody see the problem right there with B? B had 138.72 if everything could be given out as fairly as possible, which means that B should either get 138 or 139, but should never be anything different than those two numbers, and yet somehow B ended up at 140. So is this a lower quota violation or an upper quota violation? This is an upper quota violation. What do you notice about state B standard quota and final apportionment? State B illustrates an upper quota violation. Everybody see that? Okay, let's go to Monica for 5.
It turns out that Jefferson's method sometimes can be some quota violation. Where's the violation? Really favor large states.
Okay, so this is kind of a problem. Not just that it sometimes gives upper quota violations, but that it always errs on the side of giving the big states maybe more than their fair share. And what do we notice about the population of B compared to all the other states here? B is the biggest, and they're the biggest by quite a bit, actually, like 3 times the next size state. And they were the ones that ended up getting favored here. And so not only is it a problem, but it's a problem consistently favoring large states. I'm not saying I'd prefer it if it consistently favored small states, but it is biased towards large states. That's no good. So let's keep going here. We'll go to Sue-Ann. This problem? And so this was a big surprise to all our politicians. They do the calculation. New York, it has its fair share at 38.6, and somehow they end up with 40. And nobody even realized that this kind of problem might happen when we did apportionment, so we stopped using Jefferson's method as a response to this. Let's go to Ricky for Adams. Thank you. Tony, 6. Okay, so the table above was Jefferson's method. It was bad. It gave us an upper quota violation. So let's now compare the right answers, the standard quota, to the final Adams method. And do we see a problem here? What's the problem? Yeah, D should get either 138 or 139, but in actuality, this method gives B 137. So here we have a lower quota violation. For state B. And again, state B is the largest state, and in this instance, they actually got hurt by being the largest state, right? They were the ones that suffered, and they suffered because they were large. Let's go to the next page. And we'll go to Dave, 7. Thank you. Ashley, after. Okay, so then we're just kind of very quickly going through the actual history here in our United States. So it turned out Adams was never used because some folks at least had the sense to look and say, hey, does it have any potential problems before voting it in and then responding when there is a problem. So number 8 talks about Webster's method. So let's look at Webster's method. Remember, this is the one with the traditional rounding. So I will highlight those, and then the final. Are there any problems there? Everything looks okay in that one? At least nobody's off, right, by more than they would either get their lower or upper quota. All right, so any violations here? No. That doesn't mean there will never be violations. It just means in this particular example, there were no quota violations. Let's go to Eric for 9. Okay, so Webster's method turns out isn't perfect all the time. It's generally pretty close to the standard quota, but it can produce upper quota violations. It could also produce lower quota violations, but at the very least, it doesn't favor big versus small, right? So it's better in that sense, like it still has violations, but at least it doesn't consistently favor one kind of state over another. Brendan, surprisingly? Okay, thank you. Leah, are you ready? Number 10? Okay, so even our crazy, ridiculous rounding one, this Huntington Hill, can produce upper and lower quota violations. So we still, aside from Hamilton's, all these other ones can produce these violations. Let's go to Matt for 11. Okay, so again, Hamilton's method never has quota violations, but there are going to be 3 kind of really funny things that we see that go wrong, seriously wrong, with Hamilton's method. All right, let's go to Jeff again for 12. Mm-hmm. Mm-hmm. Okay, great. So we need to first find our standard divisor. We just need to do something with a couple of the numbers that are on the board. Yeah, how do we find that? So we take the population, divide it by number of seats. So 20,000 divided by 200, so we get 100. Oh, that's just super because it's really easy to divide by 100. So we don't need to even use the calculator here. So let's fill in. So this 940, everybody gets divided by that 100, right? So this becomes 9.40. Take all the populations, divide by 100, 90.30, 100.30. And of course, if we add those guys all up, we'll get the 200 seats that we want. And then remember, for Hamilton's method, what do we do with those numbers? We go all to the lower quota. So 990, 100. Add those up, 199. So that means we have how many seats left over? Just the one. And so Bama gets that one left over because they were the highest residue, right? 0.4 is bigger than the 0.3 and the 0.3. So we're going to give Bama one more, 10, and we're going to leave Tecos and Ilnos exactly where they were, 200. No problem. So that's Hamilton's method. And now we'll move to the next page. And it says, now imagine that overnight the number of seats is increased to 201. It was 200, but now we're just going to bump it up to 201, and nothing else has changed. In particular, the populations are exactly the same. We just have one extra seat. Okay, in this case, we're going to need a calculator to help us out because the new standard divisor is, again, population over seats, which becomes 20,000 divided by now 201 seats. What is this number, Matt? 99.5. So here we'll rely on you guys to do some calculations for us. So again, take each of the populations and now divide by this new divisor, the 99.5. Okay, and there's some rounding issues happening here, but if we didn't round at all, I think we'd get exactly 201 for that. And then what do we do with each of these numbers? still doing Hamilton. So we all send them down to the lower quota. We go 9, and then 90, and then 100. Total there is 199, which means we have how many seats left over? We have 2, right? Because we have 201 seats to play with. Okay, who gets the first seat? Is Illinois, because they're at 0.8, right? That's the biggest decimal. So they go up to 101, no problem. Who gets the other seat? Tecos. So Tecos goes up to 91. And what about Bama? They stay at 9. So let me just write down our answers from before. When we had 200 seats, what was the apportionment from the previous page? 10 and 90 and 100, right? So the seats went up by 1. And what happened? Bama lost a seat. Bama lost a seat. With 200 seats, Bama had 10 seats coming its way. And you're telling me that if we add a seat to the House, one of the states could go down? This is surprising, no? Like I would have expected that the right answer to this new problem would have been 10, and then either 91 or 101, right? You have one extra seat, it feels like you're just going to give that one seat to one of the other states that didn't get a seat yet. But somehow, by the way Hamilton's method worked, Bama actually went down by a seat. And so they have every reason to cry foul here, and that's the problem. So Bama lost a seat, which is really surprising. Number of seats went up, Bama's apportionment went down. Okay, 13 for Zeke. All right, so we've got this table. So this is actually what happened. This was Alabama, Texas, and Illinois, and that's where we came up with these kind of made-up names. So originally, Alabama went from 7 to 8, Texas stayed at 9, Illinois stayed at 18. But then with one additional seat being added to the House, it went from 299 to 300. Alabama actually stays at 7. Texas goes up by 1, and Illinois goes up by 1. It's exactly the same thing that we just saw here. So this happened and led to a very heated debate. And this was an illustration that maybe Hamilton's method isn't all it's cracked up to be. All right, that's one problem that might happen with Hamilton's method is this Alabama paradox. Let's go to 14 for Megan. Okay, so let's try using Hamilton's method here. We've got 5 states, or 5 planets, I guess, A, B, C, D, and E. And we're going to give these 50 seats out. So how do we find our standard divisor? Everybody see where that comes from? Total population is 900. Divided by the 50 seats, we get 18. Every 18 people you have gets you a seat. And so now we take each of our populations and divide by 18. All right, so let's get these numbers here. All right, so those are our standard quotas. Again, for Hamilton's method, we round everybody down. So we round everything down, 8, 4, 9, 11, 16. Total would have been exactly 50 before. Let's get a new total here, 20, 48. Okay, so that means we have what left over? 2 seats. So let's give the 2 seats to the people with the 2 highest decimal parts. So C and E, those are the clear winners, right? So that means that 8 and 4 stay where they are. 9 becomes 10. 11 stays. 16 becomes 17. and that's our 50. Okay, no problem, right? Everybody's happy with this apportionment. We've got peace in the galaxy. So let's move to the next page and we will see the problem. We'll go to Sarah for after. Okay, so some very small changes, new population compared to the previous one. That's like a 10-year census kind of update. So what happened to state A? Any population change? Nope. How about B? Nope. How about C? All right, so how much did C change by? I guess C went up by 8. There are 8 more people. How about D? D stayed the same, and E up by 1. Okay, fair enough. So we've got new populations. So that means we got to do our calculations again. So our standard divisor, let's hear from somebody not Sue Ann. How do we find the standard divisor here? We've got to use the 909. Where does that go? That's at the top, total population divided by still 50 seats. Okay, somebody help me out here. 18.18. All right, and I'll take standard quotas when people have them. We're using the new populations here, not the old ones. Anybody have some numbers for me? $11.22. Yep. I'm not sure if I heard that last one right. 16. Okay, anybody confirm those numbers? Good. Okay. So standard quota would be that. If we add it all up, we should perfectly get the 50, but now we have to round everybody down. So we go 8, 4, 9, 11, 16. Add those up, 48. Yes, it is. So we have 2 extra seats. Who gets the first seat? So C has a 0.95, so they're going to go up to 10. Who gets the next seat? Is B with a 0.29. That's the next biggest decimal. So they go up to 5, and everybody else stays where they were. So 8, 5, 10, 11, 16. So I'm going to box this off because that's still in the table. And now I'm going to put what the previous one was. I'll put it right up here. Can somebody just remind me what from the previous page what our final answers were? Okay. So we had peace in this universe, galaxy, whatever. And the apportionment was 8, 4, 10, 11, 17. Then 2 states went up. Which ones went up? C and E had a bigger population. What happened to the apportionment for C? Used to be 10. Still 10. Didn't change. That's kind of surprising, but whatever. I guess it's not terrible. What happened to Elysium? It went down. They had more people, and they lost the seat. For some strange reason, what about Beta? Their population stayed the same, but they gained a seat. Dugos stayed exactly the same. Their apportionment is the same. So something really funny happened here. State C gained a lot of people, didn't change at all. Elysium gained some people, but actually lost a seat. And this really seems counterintuitive. It is a surprise that the numbers happen to work out this way. So this guy also has a name. We'll go to 15 for Monica. Okay, so in particular, which state is going to complain about this new apportionment? Elysium, E. They were at 17, they gained more people, and yet they lost a seat. Not fair. Okay, 16, Sue Ann.
Started from east or north
Okay, so here we're going to have to fill in our own little labels. So we've got Northtown and Southtown. And then I guess the populations go in that next row. And I'll put totals here in the last column. Now we've got this extra column. I'm just going to put a line through it because it's not relevant here, but it will be in the follow-up to this problem. Okay, so my populations, we said north was what, 10,450? And south was 89,550. And the total there, 100,000, that's convenient. So we still need to find the standard divisor. So this time, not Sue Ann and not Monica. How do we find the standard divisor? How do we get it?
Oh, I get 100,000 divided by
100,000 population divided by the 100 trucks to give out, right? So this gives you 100, which means basically for every 100 households, you get a garbage truck. Right? Okay, so then we'll do our, what's our next row called? The standard quotas, where we take each of these guys and divide by the 100. So this is easy without the calculator, right? 104.50 and 895.50. I do that right? Oh, wait. Oh, the first one's wrong. Thank you. Both, or at least I'm consistent. All right, hold on. 100. Divided by 100, right? Oh, this is 1,000 here. Okay, thank you. So this guy is 10.45 and 89.55. All right. So we add those up, we should get perfectly the 100 garbage trucks that we have all together. That's fine. Then what do we do with those numbers? We need lower quota for both. So 10 here, 89 here. Do we need the total of those or doesn't matter? We totally need the total of those, right? 99. It's been a long day. Okay, so what does that 99 tell us? We have one seat left over. Who gets it? South, because they had a 0.55, which beats the 0.45. Super. So then our final apportionment here, we'll keep there at 10, bump this one up to 90. I don't know what we've been calling this here. I'll just call it final. And then we've given out our 100, and everybody's happy. Okay, so no problems yet, but there are about to be. Let's move on to, Sue Ann, did you read a second time? Yeah, Ricky? Okay, so before we get into the nitty-gritty details, you guys are buying this part, right? Every 1,000 people gives you another truck, yes? Every 1,000 people gives you a new truck. So if you have 5,250 new people, 5 new trucks should accommodate it. Does that seem fair? So what we are expecting is that Northtown will get their 10 and Southtown will get their 90, and these 5 additional trucks will just go right to Easttown. That is why they were put there. So just give them to Easttown, no other changes. So let's see what happens when we actually do the calculation. All right, so we're still putting north here and south here. And now it's Easttown is joining the party. Oops. Okay, and then we'll fill in the populations. All right, so they're the same as they were, but I don't see them anymore. What are they? Thank you. Okay, so there's our new total population. It was the 100,000 we had plus the 5,250 that just came in from Easttown. Okay, so then we'll find our standard divisor here. Not Suanne, not Monica, not Zeke. How do we find the standard divisor? Good. So we take the population, which was 105,250, and we divide it by, Sarah, you said 105. How come? Why? That's it. We had 100 trucks. Now we have 5 more, so 105. We do this division. What is that? 100 point. Why do I keep doing that? What is it? 1,002.38. That's probably good. Okay, and so then we're ready to find our standard quotas. Take each of the purple numbers divided by 1,002.38. I'll take them from anyone who has them. And east. Okay, can anybody confirm any of those 3 numbers for us before we move on? Okay, we've got some confirmation. So without any rounding, this total should give us the 105 buses we have, or 105 trucks we have to distribute. And again, we're doing Hamilton, so the next thing I guess is the lower quota on all of these. So we go 10, 89, and 5. And we add those up. What do we get? Yeah. Okay, so 104. So we get, so somebody gets another truck. Who gets the extra truck? Is North, because they have a .42, which is bigger than the .33 or the .23. So we go 11, 89, and 5. So is everybody happy? Who's unhappy with this new apportionment? Southtown. What happened? Isn't this strange? We gave 5 trucks to Easttown. Did they get the 5 trucks we meant to give them? Yes, it worked. Our plan was perfect. We had 5 trucks for Easttown. Wasn't going to bother anybody to just give them their 5 trucks, and we did. And yet somehow these other 2 towns that really had nothing to do with Easttown, the apportionment changed. Instead of being 10 and 90, it became 11 and 89. Another problem illustrated by Hamilton's method. So on the next page, we should have just given the trucks, but we wanted to follow our process. Tony, 17. Yes, please. Okay, so here's our summary. We looked at Hamilton's method. It's pretty clear that Hamilton's method will never violate the quota rule because of the way Hamilton's method works. But it turns out that in terms of the 3 paradoxes, we had 3 different ones that we just looked at, Hamilton's method can violate all 3. Not that they would violate all 3 in every single apportionment, but just that they can violate all 3. And does it favor anybody? Yes, it favors Hamilton's method favors the large states. Okay. So it's not that if it's not that when Hamilton's violates one of these paradoxes, it favors the large states in that violation. It's just in general, if you give it one apportionment problem, it's going to typically favor the larger states. Okay. All right. Jefferson's method. Can it violate the quota rule? Yes, it can violate the upper quota rule. It turns out that Jefferson's method will never violate any of the 3 paradoxes, so that's in favor of using Jefferson's method. Sadly, it does favor one kind of state over the other. It turns out to be large. Adams' method can violate the lower quota. Adams' method will never violate any of the paradoxes. And Adams' method favors small states. And then we go to Webster's and Huntington Hill. The bottom one is the one that we use. They both can have either kind of quota violation. They won't violate any paradox ever. And at the very least, they have the advantage over the 2 that are above it in that they don't always favor small states or always favor large states. Okay, so here's our big and sad conclusion. We'll go to Dave for it.
Turns out that produce paradoxes, any paradox violate.
Can you read that again for us?
Turns out that any portion of the pilot will produce paradoxes. This fact is called
Okay, so this is a trade-off that we are just inherently faced with anytime we try to apportion. We cannot do things fairly in any kind of sense of the word fairly, because no matter what you do, you are bound to either have something that can violate the quota rule or have something that will violate the paradoxes. It's like you got to pick your poison. There's no way to avoid both of them. Okay, so what does that mean? It means there are no perfect solutions to the problem of apportionment. This table right here, does it remind you of another topic we covered this semester? Doesn't this sound kind of like the same issues with voting theory, where we had the different ways to count the vote and then the different fairness criteria to decide if the winner was chosen fairly? And it turned out there was no way to count the vote that would always satisfy all of these fairness criteria that we talked about. Same kind of depressing news here for apportionment. There's just no way to make it so that everything works out nicely all the time. Okay, so some mnemonic devices. I think we've seen some, but not all of these. Little typo there. Hamilton's, again, I'm a vegan, so you can take that mnemonic and use it or not. I'm not going to use that one. The other ones, though, I like. Jefferson's, again, we kind of saw the J as sort of a downward arrow. Adams kind of looks like an up pointing arrow. Webster's sometimes points up, sometimes down, so you're around the traditional way. And then this last one, Huntington Hill, what the hill kind of rounding is that? I don't know. That's the really strange one, right? And that's called Huntington Hill. Okay, so the group work is as follows. A quick overview. You're going to test your understanding of the table that we just looked at with the paradoxes and the quota rule violations. And then you're going to start looking at some specific examples where you will try to demonstrate your understanding of these different paradoxes that we just saw. Raise a flag if I can help.